Alright, so today we're going to be looking at lesson 20-2. We're going to be looking at the converse of the Pythagorean theorem. So in the previous lesson we looked at the Pythagorean theorem, a squared plus b squared equals c squared. And so we start off with one of Sarah's customers designed this kite shown below. And the customer claims that it's a right triangle. And so we want to know, is this a right triangle? So the first thing that we need to do is to write the Pythagorean theorem in if-then form. So they told you the Pythagorean theorem on a couple of pages back. So if you go back in your book, they gave you your Pythagorean theorem here. It was not as an if-then statement though. It was just a statement. So what we can do is take this statement and make it into an if-then statement. It says, in any right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So what we're going to do, in any right triangle, if a triangle is a right triangle, that's where we're going to start. If a triangle is a right triangle, then the rest of that statement that they said. And so then, and I'm going to say the sum first, but you can order it in either one. Then the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. So that's your Pythagorean theorem. If you have a right triangle, then a squared plus b squared equals c squared. That's basically what they're saying. Now we want to write the converse. So converse is just where you take your hypothesis and conclusion and you switch them. So if p then q becomes if q then p. So for our converse, we're going to say if the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse then your triangle is a right triangle. So what the converse is saying, if a squared plus b squared equals c squared, then you do have a right triangle. And if a squared plus b squared does not equal c squared, then you do not have a right triangle. So, part C, we're going to use the converse of the Pythagorean theorem to determine, do we have a right triangle? So if you look, our A and our B are the 40 and the 42, because those are the smaller sides. The 58 is our C. If we have a right triangle, it's going to have to be the hypotenuse, because it's the longest side. So what we're going to do is QR squared plus RS squared equal to QS squared. So QR is 40, RS is 42, and QS is 58. And we want to see, does that equation hold true? So 40 squared is 1600, 42 is 1764. Does that equal 58 squared, which is 3,364? So if you add those two together, 3364 does equal 3364. So is it a right triangle? Yes. And the reasoning is the converse of the Pythagorean theorem. So we do have a right triangle. We are going to look at an algebraic proof. And so when it says algebraic proof, What that basically means is to show all your work and you provide a justification. So it's like you're working an equation out and you're solving to get some value. You're working some algebra out, and then you write your justification next to those. So we're going to start with our given. A squared plus b squared equals c squared. And they say, show that your Pythagorean triple, then any positive whole number multiple of these numbers is also a Pythagorean triple. So what they're telling us, a, b, and c in this given statement, all of those are positive integers. They are whole numbers. So we are going to take some random number x and multiply every term by x squared. Because if we multiply one of them by x squared, we can multiply them all by x squared. So I'm going to start by multiplying the left side of my equation by x squared, and then I'm going to multiply my right side of my equation by x squared. And the reasoning is the multiplication property of equality. So then, if you distribute, you have x squared times a squared, and then plus x squared times b squared, and then equals x squared times c squared. I think, yep. Distributive property. From there, I know that if I have x squared, a squared, I can just write x a squared. Same thing, I can write x b squared and x c squared. And so that's the power of a product property. So something that we haven't really dealt with much this year, that'd be an algebra concept. But basically, if you have two things that are being squared, you can put them in parentheses and square the quantity. And so if you look, I went from a squared, b squared, c squared to each of these being multiplied by the same number, x. So what this is saying, if you have a Pythagorean triple, so one of our Pythagorean triples is 3, 4, and 5. I can take that Pythagorean triple and multiply it by any positive whole number. So I can pick 2. If I multiply all of these numbers by 2, you get 6, 8, and 10. Since we know this is a Pythagorean triple, that means that this one is also a Pythagorean triple. And that's all that that number 2 is talking about. So let's look at number 3. Using each of the following sets of triangle side lengths, we are going to build triangles using manipulatives. I'm not going to use straws. I'm going to use a piece of paper that I have cut into 5, 6, 12, 13, and 15 centimeter lengths. And I'm going to build the triangles, and I'm going to identify them as right, acute, or obtuse, and complete the table. So, what I would recommend for you to do, if you are not going to use the straws at home, which is fine, start by filling in these 2 columns. Pause the video, get those numbers, and then we are going to work through the types of triangles that we have. So, the first column here, square of the longest segment. You're going to look and find your biggest number and then square it. So you're going to get 169. And then the sum of the squares of the 2 shorter sides. So that's the other 2 numbers. In this case, 5 and 12. And so 5 squared plus 12 squared is what we're doing. And that should also be 169. So you're going to do that for each one of these. So you should get 144 because you have 12 squared. And then 6 squared plus 6 squared is 72. On the next one, the longest one is again 12, so 144. Then we have 5 and 6. So 5 squared plus 6 squared is 61. On the next one, we have 15, so 225. And then 5 squared plus 12 squared, which is 169. Then we have 144, because 12 is our largest side. 5 and 12 is again 169. On the next one, we have 13, so 169. And then 6 squared plus 12 squared is 180. Then on the last one, we have 225. And then 6 and 12 is 180. And so now we're going to go over the type of triangle column. So here are my side lengths. I've got 15, 13, 12, 12, 6, 6, 5, and 5. And so we are going to make a triangle. The first one is using the 5, the 12, and the 13. And so if you look, it ends up being a right triangle. And by the converse of the Pythagorean theorem, if you look here, your two numbers here and here were both 169, which is what leads us to know mathematically, yes, it is a right triangle. So now let's look at the next one, 6 and 6 and 12. So this is the one that is actually the hardest one to visualize. So if you look, what ends up happening? Sometimes it might be helpful to look at the next one, the 6 and the 5 and the 12. Some people are saying it would be an obtuse triangle, but if you look, these sides don't connect. It's not a triangle at all. Like, there's no way to make these connect. So if you go back to the second one that they said, 6, 6, and 12, that is not going to be a triangle. That's just a straight line. You've got 6 plus 6, 12 on this side, and then 12 on this side. Together, they're just a straight line. They have to be greater than these two, greater than the third side to make that little triangle. So that's what your book says on that top right. To create a triangle, any two sides must be greater than the third side. But you may say, well, these are greater than 6. Always pick the smaller two numbers. These are your smallest two. Are they, when you add them together, greater than 12? No. So make sure that you are making sure they are greater than. If they're equal to, then you just have two lines either on top of each other or next to each other. So that one's not even a triangle. Then if you look, the 5 and the 6. Are 5 and 6 greater than 12? No. So again, not a triangle. Looking at 5, 12, and 15. What kind of triangle does it look like it might be? Does that look like it's greater than or less than 90 degrees? Hopefully you're seeing that's an obtuse angle right here. The next one is 5, 12, and 12. So some of you are going to say that it is an isosceles triangle, and yes it is, but it was asking about the angles. Isosceles is about the sides. So if you look, what kind of triangle is it? It is an acute triangle. Then looking at 6, 12, and 13, this one is also an acute triangle. And then the last one, 6, 12, and 15, if you look, is an obtuse triangle. So those are the different triangles that you should have from your chart. So let's fill in on our chart. We said right, not a triangle, not a triangle. Obtuse, acute, acute, and obtuse. And so some of you may have already picked up on there's a pattern, or some of you may say, but how do I do it without having to cut out pieces of paper and look at the lengths? I want to do it more quickly, and there is a shortcut. It's by looking at the numbers. So we already know if a squared plus b squared equals c squared, we have a right triangle. So I'm going to write it a little bit differently, and you'll see why in a minute. If c squared equals a squared plus b squared, then that's a right triangle. If you look at the obtuse numbers, so that's this row and this row, what do you notice about your numbers? On both of them, the square of the longest segment is the larger number. So what we can say there if the square of the longest segment, c squared, is greater than x squared plus b squared, then you have an obtuse triangle. And then if you look at the rows of the acute triangles, so that's these two, if you look on both of those, the sum of the squares of the two is greater than the c squared. So if c squared is less than a squared plus b squared, then you have an acute triangle. And so that's one way you can look at it. You can memorize those inequalities. Another option, I'm going to show you using your hands what you could do instead. So let's look. We have our hands here. Right now I have a right angle right here. And so if you imagine your hypotenuse is coming from my fingertip to my watch. If it is an obtuse triangle, if my C is bigger, that's what we just said. Watch what happens to that angle when your C gets bigger. Do you see how that becomes an obtuse angle? Okay. If your C gets smaller, what happens to that angle? It becomes an acute angle. So personally, I don't have those rules. I do have them memorized because I teach this, but you don't have to have them memorized. You can think about the figure. What happens when your C is smaller? When your C squared is smaller, you have an acute angle. What happens when your C squared gets bigger? You get an obtuse angle. So you don't have to have those inequalities memorized, and you can still work through these problems. So now let's look at 5 and 6. They want us to actually apply that concept to these numbers and determine, do we have a right triangle or not? But first it says, if it is a triangle. So let's go back. I forgot to mention, we didn't even look at these two that were not a triangle. How do these compare? The numbers compare. If you look, do you see how if you didn't check to see if they were a triangle, how you would be led to think that they were an obtuse angle because these numbers are bigger than these? So before you work through the squares, you want to check and see, are my two smaller numbers greater than my third number? Are 6 plus 6 greater than 12? No. So I didn't even need this number or that number. Same thing with 5 and 6. They don't add up to more than 12. So I didn't even need those two. So if you check to make sure that you have a triangle, it'll save you just a little bit of effort. And if you don't, you may not catch that it shouldn't be an obtuse triangle because it doesn't make a triangle. So you may end up wasting time and then get the wrong answer. So you want to check on that first. So now let's look at 5 and 6. So if you check 12 squared plus 34 squared is 144 plus 1156, which is 1300. And then our C squared is 37 squared, which is 1369. My C squared is bigger than my A squared plus B squared. So that means I have to have an obtuse triangle. Looking at B, 6 over 7 squared plus 8 over 7 squared is 36 over 49, because you can just square each term. 6 squared, 7 squared. Put them as a fraction. Same thing with this other one. 8 squared is 64, 7 squared is 49. 64 plus 49 is 100, so 100 over 49. Then my C squared is 10 over 7, so if I square that, 10 squared is 100, 7 squared is 49. Those are identical. That means I have to have a right triangle. Looking at C, 20 squared plus square root of 42 squared is 400, plus the square root of 42 squared is 42. So you have 442. Then 21 squared is 441. And so our c squared is less than our a squared plus b squared. So that means we have an acute triangle. Even though these are only one number off, it's not exactly the same. So it is not a right triangle. So now looking at number 6, we want to classify this triangle. So 27 squared, 34 squared are our A and our B. And I get 729 plus 1156, which if you add those is 1885. Then I'm looking at 45. 45 squared is 2025. And so C squared is greater than my A squared plus B squared. So that means since C squared is bigger, I have an obtuse triangle. So now looking at the next page, we want to determine whether the triangle below is right, acute, or obtuse. So the pictures are going to be misleading because they're probably going to look like they're right triangles when they draw them. And that may or may not be the case. So what you want to do is try A squared plus B squared and try C squared and see what you get. So our A and our B are 48 and 54 on this one. So I can say 48 squared plus 54 squared. And so I have 2304 and 2916. And so if you add those together, you get 5220. And then look at your C squared. 73 squared is 5,329. So my C squared is bigger than my A squared plus my B squared. So that means I have an obtuse triangle. And the reason it's obtuse is because your C squared is bigger than the other two sides added together after you square them. So now let's look at number 8. They tell us we have a Pythagorean triple, 11, 60, and 61. And we want to write two other Pythagorean triples. So, since I know that is a Pythagorean triple, pick your favorite, I would pick pick your favorite number though, and multiply all three of them by that number. If you pick 2, 11 times 2, 22, 60 times 2, 120, and 61 times 2, 122. And you can verify, but that does satisfy the Pythagorean theorem. It works in the Pythagorean theorem. Another one could be multiplying by 10 and just adding a 0 to each number because you'd multiply by 10. There are infinitely many that you could put here. You could multiply by 1,154 if you wanted to. It's just going to make you have large numbers. But you should make sure you multiply all three of the numbers by the same thing. So now let's look at number 9. Tell whether each triangle is a right triangle and justify your answer. So showing your work is fine for justification here. So when you're looking at this, you may be a little bit confused. Which one's my hypotenuse? Well, which one is the biggest number? The 65. So that is my C squared. So 65 squared, 4,225. My other two are my A squared and my B squared. So 16 squared is 256. 63 squared is 3,969. And if you add those together, you get 4,225. And so do you see how they are identical? Since they are the same thing, this is a right triangle. So what that means, 16, 63, and 65 is a Pythagorean triple. The reason I know it's a Pythagorean triple, all three of the numbers work to make a right angle, and they're all three whole numbers. So we have to have a Pythagorean triple here. Looking at part B. 25 is my largest side. So 25 squared is 625. My other two sides are 10 and 24. So 10 squared plus 24 is 100 plus 576. If you add those together, you get 676. Clearly those are not the same, so we don't have a right triangle. And it just said tell whether it was a right triangle or not. So no, it's not. if you're looking, well, what is it? My c squared is less than my a squared plus b squared. So that means I have an acute triangle. And remember, it kind of looks like a right triangle. So don't go based on what it looks like. They're going to be deceiving with the looks. So now looking at number 10. Tell whether a triangle having these lengths can be formed, and if it can be formed, is it right, acute, or obtuse? So first off, look, 36 plus 77. Those are your smaller two sides. Are they greater than 85? They are, so we do have a triangle. Now we need to look, what is 36 squared plus 77 squared? So using your calculator, you should get 7,225. And then 85 squared is also 7,225. So what kind of triangle is this? It is a right triangle. If you look at part B, they're trying to trip you up because they put 22 first. But you need to check your smaller two, 18 and 3. 18 plus 3 is only 21. Is 21 greater than 22? No. So this is not a triangle. We don't even need to look at the squares. Looking at part C, your smaller two, 33 and 56, are greater than 68. So you can look at 33 squared plus 56 squared, and that gives you 4,225. Then 68 squared is 4,624. If you see 4,624 is greater than 4,225, so that means our c squared is bigger, so we have to have an obtuse triangle. For part D, I have 6 squared plus 11 squared. 6 plus 11 is greater than 12, so I do have a triangle. And so 6 squared plus 11 squared is 157, and 12 squared is 144. So my a squared plus b squared is bigger, so that means I have to have an acute triangle. So that's how you can apply what we've been doing to just a set of numbers. Looking at number 11, Shantae is making a picture frame. Explain how she can use a ruler and the converse of the Pythagorean theorem to determine whether we meet at right angles. So what we need to do is to draw our diagonals, AC and BD. And then, once we've done that, measure the side lengths of your rectangle and your diagonals. And if it holds true for both of them when you use Pythagorean theorem, then you have right triangles. Because you had right angles, because it worked for the Pythagorean theorem. So if your side lengths, AB squared plus BC squared equals AC squared, and AD squared plus DC squared equals that's basically the same one. If BC squared plus CD squared equals BD squared, then you have two right angles because you have two triangles that work with the Pythagorean theorem, and so then your diagonals would have to be congruent. So hopefully that helps you with understanding how to use the converse of the Pythagorean theorem.